lot of you have been really doing. So this is ongoing work that we have with Eric Renaud on causality and Markovianity, information theoretic measures. So causality has been defined in specific way in time series, in particular by Nobel Prizes in economics like Granger in 1969 and Sims in 1972. Information theoretic measures of causality, like for instance transfer entropy, have been promoted recently a lot in physics, neuroscience, among other fields. And from exploring this literature, what we have realized is that, we have realized that they really discovered something. Yeah, okay, I can't distinguish. We have realized that they have discovered something that was already done in econometrics, in particular in Wiki 1984, when he looked at causality in Gaussian VAR settings, vector convergence settings, over Ehrman for Renaud 1987, which gives a more general framework for causality, doesn't restrict to Gaussianity, it doesn't restrict to linear regressions. Okay? However, both this literature, econometrics and these other fields, share the same shortcoming, which they overestimate the amount of causality. Why is this the case? Well, this is what we explore in the paper. If we start from the assumption that we have a Markov data generating process, then they measure distance between this true DGP to a set of fictitious DGP, which are the ones that are in the world without causality. So far, so good. But the issue arises because when they look for those candidates in the world without causality, they over-restrict themselves because they only look for Markov candidates. So as a result, you are trying to compute the distance from the true DGP to a smaller set of DGPs without causality, and so you end up overestimating this distance. So our paper addresses this shortcoming, and we provide some numerical evidence on this. Okay, so this is the outline of my talk. So first I'm going to define some information theoretic measure of causality, and then I'm going to go to this causality and Markovianity issue, and if we have time, which I'm not sure we have, I'll talk about some numerical evidence. Okay, so consider that we have some data for FT over T, such that we have an initial set of values that go from minus omega bar to 0, and then the sample of interest go from 1 to capital T. Okay? So consider we have a DGP, a data generating process for X and Y. Let's characterize by this joint density right here. And so this is F naught. And the notation here, to be clear, it means that we have here the variables x minus omega bar, x minus omega bar plus 1, so on and so forth, up to x capital T. Okay? And the same for y. So we can factorize the joint density this way, which is pretty standard. Okay? And if we focus on this last term right here, and this factor, we can define our first causality, which is cosine causality. So we're going to say that there is no causality from y to x in the same sense if the conditional density of y, given the past, the present, and the future values of x, and the past of y, does not depend on the future of x. So the future of x is not helping us in the prediction of y, given these other conditions. Now, when Sims look at causality, focus on this factor. However, there's this other factor here that also has some flavor of causality because we have initial values of y in the conditional distribution for x. Okay, so we define in our paper a causality measure, we call it initiation. And we said that y does not cause x in the initiation sense if the initial values of y play no role to help predict x beyond the initial values of x. Okay? Now, the question at hand is, okay, we have definitions of causality, so we need now a measure, right? So how do we do this? Well, let's define this set of density functions Hs, such that they are density functions where there is no causality from y to x in the same sense. Okay? And now what we want to do is we want to measure the distance, we want to assess how far is our true DGP F naught from this set Hs of densities without causality. Okay? And a way to do this, to measure this distance, we need some sort of measure. We use a Kullback distance. Okay? So if we use a Kullback distance for this, we can define an information theoretic measure of Sims causality, measuring the Kullback distance from F naught to these densities F that lie in this set Hs. Okay? If we solve this which is the Granger causality. Okay? Granger causality, for those of you that are not familiar with that, is just about asking this following question. Does the past of y can help in the prediction of x beyond considering the past of x? Okay? Which is what you see here. And so from this we can say that there will be no Granger causality from y to x if this guy is equal to 0, or equivalently, if there is no causality as in and no causality at initiation. Now let's go at the core of our issue, which is causality and Markovianity. Okay, so for the purpose of empirical application, we will visit the previous measures I mentioned under a maintain assumption that the true DGP follows a Markov suborder P. Okay? Now we're always going to consider that the number of initial values omega bar is greater or equal than P, which is the order of the Markov process. Now our two previous causality measures can be rewritten using this Markov assumption in the following way. So now, because we apply Markovianity here and here, we end up with only P lags in sims, okay, both numerator and denominator. But what happens in Granger is that though the denominator boils down to only having P lags, the denominator is about the marginal density of x, not the joint density, right? And since joint Markovianity of x and y does not imply marginal Markovianity of x, we are left with omega bar lags instead of just P lags. Okay? So this is a problem because it means we need to use a lot of lags in our estimation. And so Guillermo for Renault proposed to circumvent this difficulty by imposing a Markov assumption of some model Q that's going to be between P and omega bar, okay, in the definition of a process without causality. Okay? So when we are fishing for these candidates in the world without causality, they constrain themselves to Markov for the Q. What are the implications of this? Well, basically we can play the same way as before. We define a set of density functions, HG indexed by Q, which are those that are Markov processes of order Q, where there is no causality at a Granger. Okay? And so we compute the two-bucket distance between our true DGP and these DGPs that are chosen from that set. As a result, as you can expect, now the marginal of x in the denominator has only up to Q lags instead of omega bar. What are the consequences of this? Well, first corollary is that when you only use P lags, you get something that is a measure of causality is greater or equal when you use Q, when you use Q plus 1, and so forth until you use omega bar, which is the true measure of causality. So you end up overestimating the amount of causality when you restrict yourself to this Markov world in the world without causality. And second of all, we will add that this measure and the true measure and this measure indexed by Q will coincide if and only if there is no causality, and both of them will be 0. And we can measure the difference between this guy and that guy, and this difference we call it M of x, and if you look at the equation, it's measure of the amount of non-Markovianity that we have. Okay? So finally, just to mention, Guillermo for Renault is not the only paper that constrains in the world without causality to this Markov world, but also we have a Scriver 2000 proposing information theoretic measure called transfer entropy. Okay? And it assumes that x and y is jointly Markov some order P, and target the DGP, this fictitious DGP in the world without causality, among those that comply with a certain generalized Markov property, which is the one I give here, okay? Which is the conditional density of x given that P lags of x and L lags of x does not depend on this L lags of x. Okay? So as a result, in this context of transfer entropy, you also end up with these problems of overestimating the amount of causality. Okay? How much time do we have?
Just 1 minute.
1 minute. Okay. So numerical evidence, I don't have much time to cover this, but just to say that I computed everything on Mathematica, okay, all these equations, and then everything is in terms of parameters in a very simple context of a vector autoregressive model of order 1. And this is the graph we obtained for the causality measure a Granger as a function of Q, and this is the values of Q. And what you see is that